Okay, in this lecture video, now that we've seen some examples of how catalytic chemistry actually happens through covalent catalysis, acid-base catalysis, and stabilization of ions, now what we want to talk about is the details of how these types of chemistry facilitated by the enzyme lead to enhancement of the reaction rate, and also how different experimental conditions like pH, the presence of inhibitors or mutations can affect the reaction rate. So let's look at the most simplistic reaction that we can, the conversion of a substrate molecule into a product molecule. So the rate of that reaction would be then the rate constant K times the concentration of substrate. Now with enzymes, we know that we could modify this reaction scheme to be the enzyme plus the substrate first goes to form an enzyme substrate complex, which goes to form an enzyme product complex after the chemistry has happened, which then results in release of the product and regeneration of the enzyme catalyst. Now the first thing that we're going to do is we're going to make some assumptions. And the way that we know that these assumptions are going to be okay in the end is that the reaction rates that we observe and this model that we use to describe those match up. So the model that we're going to derive for how enzymes behave kinetically is supported by experimental data. So that's how we know that these assumptions are reasonable. So the first assumption that we're going to make is that the formation of the enzyme substrate complex is fast. So that builds up fast, and then it's constant. So we say that it is going to be in a steady state. So since we're in a steady state of enzyme substrate complex, we're also going to assume then that the concentration of substrate is much, much greater than the concentration of enzyme. And this assumption that the enzyme substrate complex builds up fast and then remains constant in concentration is called the steady state approximation. And what we know, why this is important, is that eventually the concentration of substrate is going to decrease over time because eventually we're just going to convert it all to product. So we're developing our model in a region where the concentration of substrate is a lot greater than enzyme so that we don't have to worry about that. So essentially what we're talking about is studying the initial rate of the reaction, which we're going to call V0. So you could think of that as the initial velocity. So in this, we're going to assume that the change in the concentration of substrate is negligible. So even though it's being converted to product, there's so much present, then it's not going to matter that its concentration is going down, that the enzyme's not going to notice that effect on its reaction rate. So if we want to graph then what it's going to look like, then the initial reaction rate, V0, as a function of the substrate concentration, it would look something like this. So the more substrate you have, the faster that enzyme is going to be able to do chemistry. It's not going to have to wait to find a substrate molecule to catalyze. The maximum velocity then that it can go, where this is going to asymptote out, is then called Vmax. That's the maximum velocity that your enzyme can go. And that happens at the point where the enzyme is completely saturated by substrate. So we're up here at the substrate concentrations where adding more doesn't matter. So you're totally saturated with with substrate. So at this point, at Vmax, the only thing limiting your enzyme, since diffusion of substrate to the enzyme is not a factor, the only thing limiting it is its ability to do the chemistry. So what we want to do is develop a mathematical relationship between the enzyme velocity and the concentration of substrate, the mathematical relationship that describes this curve. And that was done by Lenore Michaelis and Maud Menten way back in the day, and it's called the Michaelis Menten equation. So it's kind of a big deal. So in order to, again, to derive this relationship, we've got to make some assumptions. And again, we're going to find out that these assumptions are going to be reasonable based on experimental data and how it matches up with this Michaelis Menten rate equation that we're going to derive. So the first assumption that we're going to make in this derivation is that the rate limiting step in this sequence of events is the breakdown of the enzyme substrate complex. So if we rewrite enzyme plus substrate, and now I'm going to put some little rate constants on here, so forward and reverse reactions. And right now I'm going to skip the one for product release, so I'm just going to go straight to that point. And that's going to be okay in our math later on too, based on experimental data. So we're talking about K2 as the rate limiting step, so the breakdown of the enzyme substrate complex. So our second assumption then that we're going to make is we are going to assume that in the beginning, initially, the concentration of product is negligible. So we're assuming that we have no product floating around. So that means that K minus 2 is going to be negligible. So if there's no product present, we don't have to worry about that back reaction. So that's also going to mean then, therefore, that the initial reaction rate that we're going to observe is going to be K2, which is the rate limiting step, times the concentration of the enzyme substrate complex. And again, when we're talking about the rate limiting step, we're talking about the observed rate, which is of course going to be determined by the rate limiting step, the slowest step in the reaction pathway. So this is great. We now know how to talk about the rate of the reaction, the initial rate of the reaction. The problem is you can't measure the concentration of the enzyme substrate complex, right? That's being formed in solution. So therefore, we want to rewrite the concentration of the enzyme substrate complex in terms of things that we can measure, in particular, the concentration of substrate. So let's see what we know. We know that the total amount of enzyme that you have is going to be the total amount of free enzyme, not bound to anything, plus any amount of that particular enzyme that's part of the enzyme substrate complex. Then we can also write a couple of equations for the rate of formation of the enzyme substrate complex. So the rate of formation of the enzyme substrate complex is going to be K1 times the concentration of enzyme times the concentration of substrate. So I'm getting this from the beginning here, right? So it's K1 times the concentration of the enzyme times the concentration of the substrate. That's the formation of the enzyme substrate complex. And then I can also write a second equation for the rate of breakdown of the enzyme substrate complex. That's going to be equal to K minus 1, that reverse rate constant, times the concentration of the complex. So now what I'm going to do is I'm going to take the expression for number 1, and I'm going to rewrite the concentration of enzyme in terms of the concentration of enzyme total and the enzyme substrate complex. So I'm going to substitute in. So I know that K1, the rate of formation, maybe I should write that out again. So the rate of formation of the enzyme substrate complex. So now I'm substituting into my first expression. It's going to be K1 times the concentration of total enzyme minus the concentration of the enzyme substrate complex. So I'm substituting in for the concentration of enzyme in that particular expression, times the concentration of substrate. And now I'm just going to go ahead and multiply everything out through my parentheses here. So that's going to equal K1 times the concentration of total enzyme times the concentration of substrate. So you can see I'm got these parentheses here, and I'm multiplying this through, and I'm multiplying this through. So minus K1, multiply it through by the other term, times the concentration of the enzyme substrate complex, times the concentration of the substrate complex. And I can do now a similar substitution for equation number 2. Oh, oops, we got to go back. I didn't finish equation number 2. So if we come back here to the rate of breakdown of the enzyme substrate complex, we have it breaking down in the backwards direction. Let's go back. So we have this enzyme substrate complex breaking down in this direction, but we also have it breaking down in this direction. So we got to come back and add that. So here, this would be K minus 1 times the concentration of enzyme substrate complex plus K2 times the concentration of enzyme substrate complex. So that's breaking it down in the forward direction to the release of formation and release of product. Sorry about that. So now let's go back and take this equation number 2 for the breakdown of the enzyme substrate complex, and let's factor out this concentration of ES here, since it's in both equations. So do a little math to equation number 2, and we get the rate of breakdown of the enzyme substrate complex is equal to the concentration of the enzyme substrate complex times K minus 1 plus K2. So I just factored out that concentration of the enzyme substrate complex. Now we have to go back and remember that the first assumption we made in this whole process was that we were in a steady state for the enzyme substrate complex concentration. So that means if we're in a steady state, so the enzyme substrate concentration is steady state, then that means that the forward rate, so the rate of formation of it, is equal to the breakdown. So that means I can take these modified versions of equation 1 and equation 2 and set them equal to one another. So I'm going to go ahead and do that. So I'm going to get my modified math version of equation 1 was K1 times the concentration of enzyme total times the concentration of substrate minus K1 times the concentration of enzyme substrate complex times the concentration of substrate. That's going to equal the breakdown rate, which we said was K minus 1 plus K2 times the concentration of the enzyme substrate complex. Now I'm going to add this term here to both sides of my equation, because I'm just going to do some mathematical manipulations till I get a nice equation here. So now I've got K1, concentration of enzyme total, times the concentration of substrate equal to K minus 1 plus K2 times the concentration of the enzyme substrate complex, and then that term that I've added, plus K1 times the concentration of complex times the concentration of substrate. And now what I'm going to do is I'm going to simplify this, and I'm going to solve for the concentration of the enzyme substrate complex. And the reason why I'm doing that is I'm trying to figure out, remember the goal is to figure out what the concentration of the enzyme substrate complex is in terms of everything else, because I can't measure that. And that's the concentration term in my equation for the initial rate of this enzyme catalyzed reaction. So I'm trying to figure out what it is. So I'm going to come over here, and I'm going to factor this term out. So I'm just doing some algebra. So that gives me K1, concentration of enzyme total times concentration of substrate, equal to the concentration of the enzyme substrate complex times K minus 1 plus K2 plus K1 times the concentration of substrate. So now I've almost got it isolated, so if I divide both sides of my equation, both sides of my equation by this term, I think I got to go on the other next page, I find out that the concentration of the enzyme substrate complex is equal to K1 times the total concentration of enzyme times the concentration of substrate divided by K minus 1 plus K2 plus K1 times the concentration of S. So now I'm going to divide everything by K1. So I'm going to divide everything by K1 on both sides of the equation because I want to simplify all these rate constants. They're all over the place. So if I do that, I get that the concentration of the enzyme substrate complex is equal to the concentration of total enzyme times the concentration of the substrate. So remember, I'm dividing the top and the bottom, the numerator and the denominator, by K1 because that's the same thing as multiplying by 1, divided by K minus 1 plus K2 all over K1 plus the concentration of substrate. So great, I've got all of my rate constants now here in this little conglomeration, and I'm going to rename that. So we know that when you have these ratios of rate constants in forward and reverse directions, those can also be viewed then as an equilibrium constant now. That's the definition. So I'm going to call this Km. And Km is the Michaelis Menten constant. So it is the Michaelis Menten constant. And we're going to talk about that some more. And we're going to compare it to some experimental data. So what this is telling us, or the last thing we can do for substitution here, the last thing that we know is that when the enzyme is saturated, so when the enzyme is saturated with substrate, we know that it's going as fast as you can. And at that point, we are at Vmax. So when you're saturated with substrate, we also know at this point that the concentration of total enzyme that you have is equal to the concentration of enzyme substrate complex. All the enzyme is bound to substrate. If you have completely saturated your system, your enzyme, with substrate, all of it's bound. So that means if the initial rate of the reaction is equal to K2 times the concentration of substrate, then that means when we are at our maximum rate, Vmax is equal to K2 times the concentration of the total amount of enzyme. So what I'm going to do is I'm going to go back to this equation here that we've derived, and we've almost simplified it, and I'm going to multiply both sides of this reaction by K2. Okay, so both sides by K2. So if I do that, I get K2 here, and I get K2 here. But we just said that K2 times the concentration of the enzyme substrate complex is equal to V0. So if I come back over here, this becomes V0. And we also said that K2 times the concentration of total enzyme is equal to Vmax. So K2 times the total concentration of enzyme is equal to Vmax. So now I can simplify my equation again. So I'm going to take this stuff and just erase it so that you can see it. So based on the substitutions that I just made here in this equation, my Michaelis Menten equation then becomes V0 is equal to Vmax times the concentration of substrate all over the Michaelis Menten constant plus the concentration of substrate. And all of these terms in this equation can be measured experimentally. So this is the Michaelis Menten equation that will describe the kinetic behavior of an enzyme. And we're going to go through and talk about what V0, Vmax, and Km really mean and how we use them. But even though we're just going to use this equation now, it's important to understand that the assumptions that it's based upon, because they were really important in the derivation of this kinetic model.